Welcome to Galaxy Guru, your go-to channel for all things cosmic. Today, we're setting off on an incredible adventure to the farthest reaches of the universe. Picture this. We're not just looking at distant stars or nearby galaxies, we're peering back billions of years to when the universe was a mere toddler, still figuring out how to tie its cosmic shoelaces. We're talking about the farthest galaxies ever discovered, ancient beacons of light that have traveled unimaginable distances to reach us. These aren't just twinkling dots in the sky. They're time capsules, each one holding secrets from the universe's wild and chaotic infancy. They're the opening chapters in the grand saga of cosmic evolution, and they spark a sense of wonder that makes you feel both tiny and connected to something vast. So, what are these distant galaxies? How do we find them, and why should we care? Grab your imaginary spacesuit and let's blast off to find out. Part 1. Peering into the cosmic dawn. What are the farthest galaxies? Let's start with the basics. The observable universe. This is the chunk of the cosmos we can actually see from our little blue planet. It's not infinite. Our view is limited by the speed of light and the universe's age, which clocks in at about 13.8 billion years. You might think, okay, so the farthest we can see is 13.8 billion light years, right? Well, not quite. The universe has been expanding ever since the Big Bang, stretching space itself like a cosmic rubber band. This means the light from those far-off galaxies has been traveling toward us while the galaxies themselves have been moving farther away. The result? The actual distance to these galaxies today is much greater than 13.8 billion light-years, more like 46 billion light-years across the observable universe. It's like trying to measure the distance to a friend who's running away from you while you're stuck in slow motion. This expansion also means that when we look at these distant galaxies, we're not seeing them as they are now, but as they were billions of years ago. It's a bit like getting a postcard from the past. For example, the light from the sun takes 8 minutes to reach us. So we see the sun as it was 8 minutes ago. Now scale that up. When we spot a galaxy 13 billion light years away, we're seeing it as it was 13 billion years ago, when the universe was a chaotic soup of gas and baby stars. It's a cosmic time machine, letting us peek at the universe's awkward teenage phase, pimples, growth spurts, and all. The farther we look, the closer we get to the Big Bang, that explosive moment when space, time, and everything we know kicked into gear. How wild is that? So, how do we measure these mind-boggling distances? That's where redshift comes in, and it's one of the coolest tools in an astronomer's kit. Redshift, often written as Z, happens because the universe is expanding. As space stretches, the light waves from distant galaxies stretch too, shifting toward the red end of the spectrum. Think of it like the sound of an ambulance siren. As it drives away, the pitch drops because the sound waves are stretched out. This is called the Doppler effect, and it works for light in a similar way. The more the light is stretched, the higher the redshift, and the farther away the galaxy is. A redshift of Z equals 1 means the light's wavelength has doubled since it left the galaxy. Z equals 10 means it's stretched tenfold. It's like the universe is playing a game of telephone, whispering secrets from the past in a deeper and deeper voice. Let's break it down with some numbers. A galaxy at Z equals 1 is roughly 7.7 billion light years away, showing us the universe as it was about halfway through its history. But the farthest galaxies? They're at redshifts of z equals 10, z equals 12, even z equals 14 or more, putting them over 13 billion light years away, back when the universe was just a few 100 million years old. That's less than 5% of its current age. Imagine looking at a photo of your great-great-grandparents as babies. That's the kind of time travel we're doing here. And here's a fun fact. The light from these galaxies has been traveling so long that when it started its journey, Earth wasn't even a twinkle in the universe's eye. The sun, the planets, the dinosaurs, none of them existed yet. It's humbling to think that this light has been racing across space for billions of years just to land in our telescopes. Why do these far-flung galaxies matter? They're more than just pretty lights. They're the missing pieces of a cosmic puzzle. These are the oldest galaxies we've ever seen, formed in the universe's first few 100 million years. Studying them is like digging into an archaeological site, uncovering clues about the conditions right after the Big Bang. How did the first stars spark to life? What was the universe like before it had planets or people? These galaxies hold the answers. They're also key to understanding how galaxies evolve. Picture them as the tiny seeds that grew into the massive, swirling galaxies we see today, like our own Milky Way. By looking at their size, shape, and the way they churn out stars, we can trace the family tree of every galaxy in the sky. But it's not just about history. They tackle some of the biggest mysteries in science. For instance, they help us explore the era of re-ionization, when the universe went from a foggy, neutral haze to a clear, ionized state lit up by the first stars. They also shed light on dark matter, that invisible stuff that helped pull these galaxies together. Without dark matter's gravitational glue, these early galaxies might never have formed. It's like finding the recipe for the universe's first cake: stars, gas, and a pinch of mystery. Plus, they give us a glimpse into the physics of the early cosmos, testing our theories about how gravity, light, and matter behave under extreme conditions. Spotting these galaxies, though, is a Herculean challenge. They're so far away and so faint that detecting them is like trying to hear a whisper from the other side of the planet. Enter the heavy hitters: the Hubble Space Telescope and the James Webb Space Telescope, JWST. Hubble has been our cosmic eye for decades, capturing stunning images like the Hubble Ultra Deep Field, where a tiny patch of sky revealed thousands of galaxies stretching back billions of years. But Hubble's vision fades in the infrared, where the light from the farthest galaxies hides. It's like trying to read a book in the dark. You need a better flashlight. That's where JWST shines, literally. Launched in 2021, this infrared powerhouse can see through cosmic dust and pick up the faintest glimmers from the universe's edge. It's equipped with cutting-edge tech like adaptive optics, which corrects for Earth's blurry atmosphere, and it uses tricks like gravitational lensing, where massive objects bend and amplify light to spot these distant gems. JWST has already shattered records, finding galaxies at z equals 14 and beyond, dating back to just 290 million years after the Big Bang. It's like upgrading from a magnifying glass to a superpower microscope, revealing a universe we barely knew existed. In the next part, we'll meet some of these galactic record breakers. Take GNZ11, discovered in 2016, with a redshift of z equals 11.09. That's 13.4 billion light years away, showing us a galaxy just 400 million years after the Big Bang. It's tiny, about 25 times smaller than the Milky Way, but it was pumping out stars at a furious pace. Then there's JWST 14-0, spotted by JWST at Z equals 14.32, a mere 290 million years post-Big Bang. These galaxies are rewriting the textbooks, proving star formation kicked off earlier than we thought. And they're not alone. Galaxies like MAX 0647-JD, amplified by gravitational lensing, hint at an even deeper cosmic past. Each one is a treasure trove of data, telling us about star birth, galaxy growth, and the universe's wild youth. So, what's the big takeaway? These farthest galaxies connect us to the universe's dawn. They're not just about the past. They hint at the laws of physics that govern everything, from the tiniest atoms to the grandest galaxies. As JWST keeps hunting, who knows what we'll find next? Maybe a galaxy at Z equals 15, or evidence of the very first stars. It's a golden age of discovery, and we're all along for the ride. In part 2, we'll dive into the tech and tricks behind this cosmic scavenger hunt. How do we even catch these ancient lights? Spoiler, it involves some seriously clever science. Stick around and let's keep exploring the edge of the universe together. In part 1, we kicked off our epic journey to the edge by marveling at the farthest galaxies, those ancient glowing time capsules from billions of years ago. We talked about why they're a big deal, but now it's time to answer the real head-scratcher. How do we even find these things? These galaxies are so distant, so faint, and so mind-bogglingly old that spotting them is like trying to hear a mouse sneeze from the other side of the Milky Way. In part 2, we're pulling back the curtain on the incredible tools, tech, and human grit that make this galactic treasure hunt possible. From legendary telescopes like Hubble to the infrared wizardry of the James Webb Space Telescope, JWST, we're about to uncover the secrets of the cosmic detective game. So grab your star charts and let's dive in. This is going to be a blast. Part 2. The Great Galactic Hunt. How we track the farthest galaxies. First stop. The tools of the trade. You can't hunt the universe's oldest galaxies with a pair of binoculars or that rusty scope in your attic. Nope. We're talking about the heavyweights of astronomy. Telescopes that are basically superheroes in metal and glass. Let's start with the OG legend, the Hubble Space Telescope. Launched way back in 1990, Hubble's been orbiting Earth like a trusty cosmic watchdog for over 3 decades. Why put it in space? Simple. Earth's atmosphere is a blurry mess for stargazing. It's full of air currents, water vapor, and city lights that smear the view like a smudged windshield. Hubble sits above all that, about 340 miles up, giving us a razor-sharp look at the universe. It's like trading a foggy pair of glasses for a high-def TV. Hubble's resume is stacked. Ever heard of the Hubble Deep Field? In 1995, astronomers pointed it at a tiny, boring-looking patch of sky, about the size of a pinhead held at arm's length, and told it to stare for 10 days straight. The result? A jaw-dropping image packed with over 3,000 galaxies, some so far away, they date back 12 billion years. It's like aiming your camera at a blank wall and discovering a hidden mural of cosmic history. Hubble also gave us the iconic Pillars of Creation, those towering gas clouds in the Eagle Nebula, and countless other snapshots that make you go, whoa, space is wild. But here's the catch. Even Hubble has its kryptonite. The light from the farthest galaxies gets stretched by the expanding universe into infrared wavelengths, and Hubble's not great at seeing that. It's like trying to tune into an AM station with an FM radio. You get static, not the full song. Enter the James Webb Space Telescope, or JWST, Hubble's slick, high-tech successor. Launched on Christmas Day 2021, JWST is the ultimate cosmic upgrade. Picture this: a 6.5-meter mirror made of 18 gold-coated hexagonal segments that unfold in space like an origami masterpiece. That mirror is huge, 3 times wider than Hubble's, and it's built to soak up faint infrared light like a sponge. Why gold? It reflects infrared better than silver or aluminum, making JWST a heat-seeking missile for ancient galaxies. And speaking of heat, JWST hangs out a million miles from Earth at a spot called L2, where it uses a giant sunshield. Think of it as a 5-layer cosmic beach umbrella to stay super cold. That chill factor lets it detect the tiniest infrared whispers from the universe's edge. It's like giving astronomers night vision goggles after years of squinting in the dark. So, we've got these powerhouse telescopes. How do they figure out which galaxies are the farthest? The magic word is redshift, or Z for short. We touched on this in part 1, but let's dig deeper. Redshift happens because the universe is expanding, stretching the light from distant galaxies like a rubber band. The farther the galaxy, the more stretched the light, shifting it from visible colors to red, and eventually infrared. A redshift of Z equals 1 means the light's wavelength has doubled. Z equals 11 means it's stretched 12 times over. It's our cosmic ruler, telling us both distance and age. For example, a galaxy at Z equals 11 is about 13.4 billion light-years away, showing us the universe when it was just a toddler, 400 million years old. But measuring redshift isn't like sticking a tape measure into space. Astronomers use spectroscopy, splitting a galaxy's light into a rainbow to spot specific patterns, like hydrogen's glowing fingerprints. These patterns shift with redshift, and by measuring that shift, we calculate Z. Sounds easy, right? Not so fast. For nearby galaxies, it's a breeze, but the farthest ones are so dim that their light is a mere trickle. Imagine trying to read a book by the glow of a dying firefly. That's the challenge. Take GNZ 11, once the farthest known galaxy at Z equals 11.09. Astronomers stared at it with Hubble for over 12 hours, using a grism, a combo of a grating and prism, to tease out its spectrum. Even then, the signal was so faint, they had to use math wizardry to confirm it. JWST, though, is a redshift rockstar. Its near-infrared spectrograph, NIR spec, can nail down Z values for galaxies at Z equals 14 and beyond in a fraction of the time. It's like swapping a magnifying glass for a microscope. Suddenly, the details pop. Telescopes are just the start. Astronomers have some sneaky tricks up their sleeves to spot these elusive galaxies. One of the coolest is gravitational lensing. Here's how it works. Massive objects like galaxy clusters have so much gravity that they bend space-time, acting like a giant lens. Light from a distant galaxy behind the cluster gets warped and magnified, making it easier to see. It's like holding a magnifying glass over a tiny bug. Suddenly, you can spot every detail. The galaxy MAX 0647-JD at Z approximately 11 was found this way, boosted by a cluster's gravity. Without lensing, it'd be a ghost in the noise. Einstein predicted this trick over a century ago, and now it's a galactic cheat code. Then there's the battle against cosmic noise. Space isn't a quiet void. It's a bustling mess of stray light, dust, and foreground galaxies. To cut through it, astronomers use long exposures and multi-wavelength imaging. The Hubble Ultra Deep Field took 11 days of staring to capture light from billions of years ago, stacking images to build a clear picture. It's like leaving your camera open to catch fireflies on a summer night. Patience pays off. JWST takes it further with its infrared vision, piercing through dust clouds that block visible light. Think of it like adding X-ray specs to your toolkit. Hidden galaxies leap into view. The human touch. Teamwork makes the dream work. Let's zoom out for a sec and salute the humans behind the hunt. Discovering a galaxy like GNZ11 wasn't just Hubble's doing. It took a global posse of astronomers, engineers, and data crunchers. They paired Hubble's data with ground-based giants like the Keck Observatory in Hawaii and the Spitzer Space Telescope, piecing together clues like cosmic detectives. There were late nights, heated debates, and double checks galore to rule out flukes. JWST's launch was even bigger. Decades of planning, $10 billion, and thousands of people across continents. Every bolt, every line of code, every observation. It's a monument to human curiosity, chasing the unknown. What's next? The edge keeps moving with JWST in full swing. We're in a golden age of galaxy hunting. It's already smashed records, spotting JDIS GSZ, 14.32 at seed equals 14.32, just 290 million years after the Big Bang. That's earlier than we thought galaxies could even form. Projects like the JDIS survey are scouring the sky for more, and who knows, by next year, we might hit Z equals 15. These finds aren't just trophies, they're shaking up our cosmic story. Some of these early galaxies are shockingly bright and beefy, hinting that star formation revved up fast. It's like finding a kindergartner who's already a pro athlete. Astronomers are scrambling to explain it. As we wrap part 2, let's soak in the scale of this adventure. We're catching light that's traveled 13 billion years, older than our planet, older than our sun. It's humbling and thrilling all at once. Next up, in part 3, we'll spotlight GNZ11, the galaxy that held the distance crown for years. How'd it get found? What's it like? And what's it still teaching us? Stay tuned for GN-Z11, the galaxy that shattered records. Imagine peering through a window into the universe's infancy, catching a glimpse of a time when the cosmos was just a toddler, barely 400 million years old. That's what GNZ11 offers us, a galaxy so distant and ancient that it holds the record as the farthest object humanity has ever observed with detailed precision. Discovered in 2016, GN-11 isn't just a faint smudge in the sky. It's a treasure trove of cosmic history, a snapshot of the universe's wild, formative years. In this part, we'll dive deep into its discovery, unravel its scientific significance, compare it to other galaxies, and celebrate the human ingenuity behind this breakthrough. Part 3. GNZ11, a cosmic record breaker. The discovery, a needle in a cosmic haystack. GNZ11 didn't announce itself with fanfare. It was found lurking in data collected by the Hubble Space Telescope, a workhorse of astronomy since its launch in 1990. The galaxy emerged from the Goods North Survey, a meticulous mapping of a small patch of sky in the constellation Ursa Major. Astronomers, led by Pascal Oesch of Yale University, weren't just browsing the cosmos. They were hunting for the most distant galaxies, pushing Hubble to its limits. The key to spotting GNZ 11 was its redshift, a measure of how much its light has been stretched by the universe's expansion. Light from GNZ 11 has a redshift of 11.1, meaning it's been stretched so far that what was once ultraviolet light now appears in the infrared. To put that in perspective, a redshift of 11.1 corresponds to a time when the universe was just 3% of its current age, about 13.4 billion years ago, or roughly 400 million years after the Big Bang. Detecting this required Hubble's Wide Field Camera 3, an instrument sensitive to infrared wavelengths, paired with a technique called slitless spectroscopy, which spreads light into a spectrum without needing a traditional slit, ideal for faint, distant objects. The challenge was immense. GNZ 11 is 25 times smaller than our Milky Way and 100 times less massive. Yet it shines with surprising brightness due to ferocious star formation. Finding it was like spotting a firefly across a continent on a moonless night. The team poured over hundreds of hours of observation data, battling cosmic noise and the faintness of such a distant source. Their persistence paid off when GNZ 11's spectral signature confirmed its distance, smashing the previous record held by a galaxy at redshift 8.68. We were stunned, Osh later recalled. It was like finding a living fossil from the universe's dawn. The name GNZ 11 isn't poetic. It's a catalog label. GN stands for Goods North, and Zeta 11 reflects its redshift of 11. Think of it as a cosmic barcode, practical but packed with meaning. Why does GNZ 11 matter? It's not just its distance, it's what it reveals about the universe's adolescence. At 400 million years post-Big Bang, we're peering into the epoch of re-ionization, a murky period when the first stars and galaxies began lighting up the cosmos, burning away a fog of neutral hydrogen. GNZ 11 is a rare survivor from this era, offering clues about how galaxies formed and evolved when the universe was a chaotic nursery. Age and distance. Traveling at the speed of light, the photons we detect from GNZ 11 left it 13.4 billion years ago. But because the universe has been expanding, GNZ 11 is now about 13.4 billion light years away in terms of light travel distance. Its comoving distance, accounting for expansion, is closer to 32 billion light years, a mind-bending reminder that space itself stretches. Picture it like a raisin in a rising loaf of dough. As the dough expands, the raisin drifts farther away, even if it's not moving. Size and structure. GNZ 11 is a compact galaxy, spanning just 4,000 light-years across, tiny compared to the Milky Way's 100,000 light-year diameter. If the Milky Way is a sprawling metropolis, GNZ 11 is a bustling village. Yet its small size belies its energy. Hubble data suggest it's forming stars at a rate 20 times higher than the Milky Way today, despite having only 1% of our galaxy's mass. That's like a single factory outproducing an entire industrial city. This frenzied star formation hints at a universe in overdrive, where gas clouds collapsed rapidly into stars under conditions vastly different from today's calmer cosmos. Star formation and chemistry. The stars in GNZ 11 are likely massive, hot, and short-lived, forged from pristine gas with almost no heavy elements, just hydrogen and helium from the Big Bang. Astronomers infer this from its brightness and lack of heavy element spectral lines, suggesting a population 3 star population, the first generation of stars theorized to kickstart cosmic evolution. It's as if GNZ11 is a time capsule, preserving the raw ingredients of the early universe before metals like carbon and oxygen became common. Think of GNZ11 as a baby photo of the universe. Just as a newborn's features hint at their future growth, GNZ11's properties, its size, star formation rate, and chemistry offer a glimpse of how galaxies matured into the grand spirals and ellipticals we see today. To appreciate GNZ11's uniqueness, let's stack it up against its peers, both nearby and distant. The Milky Way. Our galaxy, with its 200 billion stars and stately spiral arms, is a middle-aged adult compared to GNZ11's infancy. The Milky Way forms about 1 solar mass of stars per year, a leisurely pace next to GNZ11's 20 solar masses annually. The Milky Way's vast size and metal-rich stars reflect billions of years of evolution, while GNZ11 is a snapshot of raw potential, untouched by time. Andromeda, M31. Andromeda, our closest galactic neighbor at 2.5 million light-years, is another giant, slightly larger than the Milky Way. Its star formation has slowed, and its structure is well-defined, a stark contrast to GNZ11's compact, chaotic brilliance. Andromeda's proximity lets us study it in detail, but GNZ11's distance makes it a harder, more precious puzzle. Other distant galaxies. Before GNZ11, the record holder was EGSY 8p7 at redshift 8.68, about 570 million years after the Big Bang. GNZ11 pushes us 170 million years closer to the Big Bang, a significant leap in cosmic archaeology. Other candidates like MAX 0647-JD, redshift approximately 11, have been spotted via gravitational lensing, but GNZ11's spectroscopic conformation makes it the gold standard. It's the yardstick against which we measure the early universe. If GNZ11 were placed next to the Milky Way, its light would be so faint we'd need a telescope like Hubble to see it. Even at close range, its distance dims it by a factor of billions. The human element, astronomers in awe. Behind GNZ11's discovery is a team of humans driven by curiosity. Pascal Oesch and his colleagues at Yale, alongside collaborators from the Space Telescope Science Institute, spent years refining Hubble's data. It felt like we were explorers charting uncharted waters, said Gabriel Brammer, a co-author. Their work wasn't just technical, it was emotional. The moment GNZ11's redshift was confirmed, the team knew they'd rewritten the record books. The discovery also sparked debate. Some wondered if GNZ11's brightness meant it was an outlier, challenging models of early galaxy formation. Others saw it as proof that galaxies formed faster and brighter than expected. This human story of doubt, triumph, and wonder mirrors the scientific process itself. GNZ11 is a marvel, but it's not the end of the story. The James Webb Space Telescope, JWST, launched in 2021, promises to peer even deeper, potentially spotting galaxies at redshift 15 or beyond, closer to the Big Bang's first light. In Part 4, we'll explore how JWST is rewriting our cosmic history, building on GNZ11's legacy. For now, GNZ11 stands as a testament to human ingenuity and the universe's vastness, a tiny, brilliant spark from a time when the cosmos was young, wild, and full of possibility. Thanks for sticking with me and for all the new subs, I truly appreciate it. Okay, everyone. In part 3, we marveled at GNZ 11, the galaxy that held the record as the farthest known object for years, shining a light on the universe's wild, formative days just 400 million years after the Big Bang. But as incredible as GNZ 11 is, it's no longer the farthest galaxy we've ever seen. Thanks to the James Webb Space Telescope, JWST, we've now spotted galaxies that make GNZ 11 look like a cosmic neighbor. These new discoveries are rewriting the history of the universe, pushing the boundaries of what we thought was possible. So, buckle up. Today, we are diving into JWST's Galactic Goldmine, where we'll meet galaxies so distant they're practically from another era. Let's blast off and see what lies beyond the edge. Part 4. JWST's Galactic Goldmine, Pushing the Boundaries. The JWST Revolution. A new era of discovery. Before we meet these record-breaking galaxies, let's take a moment to appreciate the machine that made it all possible. The James Webb Space Telescope. Launched on Christmas Day 2021, JWST is the most powerful space telescope ever built, and it's been a game-changer for astronomy. Unlike its predecessor Hubble, which primarily observes in visible and ultraviolet light, JWST is designed to see in the infrared spectrum. Why does that matter? Well, remember our old friend redshift? As light from distant galaxies travels through the expanding universe, it stretches into longer wavelengths, shifting from visible light to infrared. So, to see the farthest galaxies, we need a telescope that can detect those stretched out waves. JWST is like a cosmic night vision goggles, revealing galaxies that Hubble could only dream of. But JWST isn't just about seeing in infrared, it's a technological marvel. Its primary mirror is a whopping 6.5 meters across, made up of 18 hexagonal segments coated in gold to reflect infrared light. These segments unfold in space like a high-tech flower, creating a mirror 3 times larger than Hubble's. And to keep its instruments cool enough to detect faint heat signatures from billions of years ago, JWST orbits 1 million miles from Earth at a point called L2, where it uses a massive sun shield, about the size of a tennis court, to block out the sun's warmth. It's like a cosmic detective, equipped with the best gear to solve the universe's oldest mysteries. Redshift, revisited, measuring the unmeasurable. To understand just how far these new galaxies are, we need to revisit the concept of redshift. In part 1, we learned that redshift, or Z, measures how much a galaxy's light has been stretched by the universe's expansion. The higher the Z, the farther away and older the galaxy. GNZ 11, with its Z equals 11.09, was a jaw-dropper. But JWST has found galaxies at Z equals 13, Z equals 14, and even beyond. Let's break that down. A galaxy at Z equals 13, for example, means its light has been traveling for about 13.5 billion years, showing us the universe when it was just 300 million years old. That's less than 2% of its current age. It's like looking at a photo of your great-great-great-grandparents before they even met. And here's the kicker. Because the universe has been expanding, these galaxies are now much farther away than the light travel time suggests. A galaxy at Z equals 13 is actually about 33 billion light years away in terms of its current distance. It's a mind-bending reminder that space itself is growing, carrying these galaxies farther from us even as their ancient light finally reaches our telescopes. But measuring redshift for these faint galaxies isn't easy. It requires spectroscopy, splitting the galaxy's light into a spectrum to identify specific features like the glow of hydrogen atoms, For GNZ11, Hubble had to stare for over 12 hours to get a decent spectrum, and even then, it was a struggle. JWST, however, is a redshift hunting machine. Its near-infrared spectrograph, NIR spec, can capture spectra from dozens of galaxies at once with sensitivity that Hubble could only envy. It's like upgrading from a flip phone to a smartphone. Suddenly, everything's faster, clearer, and way more powerful. Meet the new record holders, galaxies beyond GNZ11. So what has JWST found? Let's meet some of the new champions of distance. One of the most exciting discoveries is JWST 14-0, a galaxy at a redshift of ZD equals 14.32, confirmed in 2023. That places it a mere 290 million years after the Big Bang, making it the farthest galaxy with a spectroscopically confirmed distance as of 2025. To put that in perspective, when this galaxy's light began its journey, the universe was still in its cosmic diapers, with stars and galaxies just starting to flicker into existence. But JD's JS 14-0 isn't alone. JWST's JD survey, short for JWST, Advanced Deep Extragalactic Survey, has uncovered a treasure trove of high redshift galaxies, with candidates at Z equals 15 and beyond. These galaxies are tiny, some just a few hundred light years across compared to the Milky Way's 100,000 light-year span, but they're bursting with activity. Despite their small size, they're forming stars at a breakneck pace, sometimes 10 to 20 times faster than galaxies today. It's like finding a toddler who's already running marathons, astonishing and a bit confusing. One of the most intriguing finds is Glass Z13, another JWST discovery at Z approximately 13, which shows signs of surprisingly mature features. Early analysis suggests it might have a disk-like structure, something we'd expect in much older galaxies. This has astronomers scratching their heads. How did these galaxies grow up so fast? It's like seeing a kindergartner solving calculus problems. Impressive, but it challenges everything we thought we knew about galaxy formation. What these galaxies tell us about the early universe. These discoveries aren't just about setting records, they're rewriting the story of the universe's first chapters. For decades, astronomers believed that galaxies formed slowly, taking their time to build up stars and structure. But JWST's findings suggest that the early universe was a hotbed of activity, with galaxies popping up faster and brighter than expected. Some of these galaxies are so luminous that they defy current models, hinting that we might need to rethink how stars and black holes behaved in the cosmic dawn. Take Jade's GSZ 14-0 for example. Its brightness suggests it's packed with massive hot stars, possibly including the elusive population 3 stars, the first generation of stars made purely of hydrogen and helium. These stars were theorized to be enormous, burning hot and fast, and their existence would be a holy grail for astronomers. If confirmed, it would be like finding the universe's first campfire, sparking the light that would eventually fill the cosmos. Another puzzle is the presence of heavy elements. Galaxies at Z greater than 10 should be pristine, with almost no metals. In astronomy, metals mean anything heavier than helium. But some JWST observations hint at traces of oxygen and carbon in these early galaxies, suggesting that star formation and supernova explosions, which produce heavy elements, might have kicked off even earlier than we thought. It's like discovering that your newborn already has a full set of teeth. Unexpected and a bit unsettling. the technology behind the magic. How does JWST pull off these cosmic feats? Let's geek out on the tech for a second. JWST's primary mirror is a marvel, 6.5 meters of gold-coated beryllium, folded up for launch and unfurled in space like a high-tech flower. Each of its 18 segments is adjustable to within a fraction of a human hair, ensuring razor-sharp focus. But the real star is its suite of instruments like the mid-infrared instrument, MIRI, which can see through dust clouds that block visible light, revealing hidden galaxies like a cosmic X-ray. Then there's NIRCam, the near-infrared camera, which can snap images in multiple wavelengths at once, allowing astronomers to map the universe's structure in unprecedented detail. And don't forget about the fine guidance sensor, which keeps JWST locked onto its targets with pinpoint accuracy, even as it orbits 1,000,000 miles from Earth. It's like threading a needle from across the solar system, precision on a whole new level. But JWST isn't working alone. It builds on decades of data from Hubble, Spitzer, and ground-based telescopes like the Atacama Large Millimeter Array, ALMA, which can detect the cool gas and dust in distant galaxies. Together, these tools create a multi-wavelength view of the cosmos, like assembling a puzzle with pieces from different boxes. It's a testament to human collaboration and ingenuity, with thousands of scientists, engineers, and dreamers working toward a shared goal. Challenges and limitations. The edge of knowledge. As thrilling as these discoveries are, they come with challenges. For one, confirming redshifts for these faint galaxies is tricky. Spectroscopy requires a lot of light, and even JWST needs long exposure times to capture enough photons. For galaxies at Z greater than 14, we're often dealing with just a handful of pixels on a detector, making it hard to distinguish real signals from noise. It's like trying to identify a whisper in a crowded room. You need to be patient and precise. There's also the issue of cosmic variance. The universe isn't uniform. Some regions are denser than others, which can skew our understanding of how common these early galaxies are. Plus, gravitational lensing, while helpful, can distort and amplify light in unpredictable ways, complicating distance measurements. It's a reminder that science is messy, and every discovery comes with caveats. But perhaps the biggest challenge is interpreting what we see. These galaxies are so different from anything we know that our models struggle to keep up. Are they really as bright as they seem? Or is there something we're missing? Could there be exotic objects like primordial black holes masquerading as galaxies? The answers are still unfolding, and that's part of the excitement. Each new observation is a clue in a cosmic mystery. To bring this to life, let's hear from the scientists themselves. JWST is like opening a new window into the universe, says astrophysicist Jane Rigby, JWST's operations scientist. We're seeing things we never imagined, and it's both exhilarating and humbling. Another researcher, Brant Robertson from UC Santa Cruz, adds, "These galaxies are challenging everything we thought we knew about the early universe. It's a golden age of discovery." Their words capture the awe and uncertainty of this moment in astronomy. We're not just collecting data. We're rewriting the story of how the cosmos came to be. As we wrap up Part 4, we've seen how JWST is pushing the boundaries of what's possible, uncovering galaxies that challenge our understanding of the universe's first days. But what do these galaxies actually look like? Are they majestic spirals like the Milky Way? or something entirely different? In part 5, we'll explore the bizarre shapes, sizes, and behaviors of these cosmic infants. It's going to be a wild ride. Alright, my friends, we've really been hurtling through space and time on our epic journey to the edge. In part 4, we geeked out over how the James Webb Space Telescope, JWST, is spotting galaxies so distant they make our previous record holder, GNZ11, seem like it's practically in our backyard. These galaxies hail from a time when the universe was just a cosmic toddler, only a few 100 million years old. But what do these ancient relics actually look like? Are they stunning spirals like the Milky Way, or something far stranger? Spoiler alert: they're weird, wild, and totally unlike anything nearby. In part 5, we're diving deep into the quirky shapes, sizes, and behaviors of these cosmic infants, with extra juicy details to satisfy your curiosity. Buckle up. Let's blast off into the unknown. Part 5. Cosmic infants. What do the farthest galaxies look like? The size. Surprise, tiny titans of the early universe. Let's kick things off with size. If you're imagining these farthest galaxies as vast, majestic systems like the Milky Way, hit the brakes. These cosmic infants are tiny by today's standards. Take GNZ11, one of the most distant galaxies we've pinned down. It's a mere 4,000 light-years across. Compare that to the Milky Way's sprawling 100,000 light-year wingspan, and GNZ11 is just 4% of our galaxy's size. It's like comparing a cozy studio apartment to a sprawling estate. And GNZ11 isn't even the smallest. Some of these early galaxies shrink down to just a few hundred light-years across, barely qualifying as galactic runts. But don't let their petite stature fool you. These little dynamos are mighty. GNZ11, for example, is churning out stars at a rate 20 times higher than the Milky Way, despite having only 1% of our galaxy's mass. Picture a tiny espresso machine outpacing a giant coffee factory. It's efficiency on steroids. How do they pull this off? In the early universe, these galaxies were swimming in vast, pristine clouds of gas, mostly hydrogen and helium, leftovers from the Big Bang. These clouds collapsed under gravity's pull, igniting frenzied bursts of star formation. It's as if the universe hit the fast-forward button, packing as much action as possible into its chaotic youth. Shapeshifters, cosmic chaos in full display. Now, let's talk shape. If you love the graceful spiral arms of the Milky Way or the sleek elliptical curves of Andromeda, brace yourself. The farthest galaxies are a hot mess. Forget orderly disks or elegant arms. These cosmic infants are clumpy, irregular blobs. JWST images show them as smudged patches of light, with stars and gas scattered in wild, unpredictable patterns. It's like the universe was still in art class, doodling rough sketches before mastering the galaxy blueprint. Why so chaotic? Back then, galaxies were in their awkward teenage phase, constantly crashing into each other, merging, and stirring up their insides. These collisions scrambled their gas and stars, preventing them from settling into stable shapes. Imagine two kids smashing their Lego sets together. You don't get a sleek spaceship, just a glorious jumble. Yet, amid the chaos, there's a strange beauty. JWST reveals glowing knots of star formation within these blobs, like sparkling jewels in a messy treasure chest. Some even show faint hints of structure, tiny bars or wisps, suggesting the earliest steps toward the galaxies we know today. Star formation on steroids, a cosmic baby boom. One of the wildest traits of these distant galaxies is their star-forming frenzy. The Milky Way plods along, forming about 1 solar mass of stars per year, steady, reliable, like a slow cooker recipe. Meanwhile, galaxies like GN-Z11 are blasting out 20 to 30 solar masses annually, and some JWST finds at redshift Z equals 14 might be even more extreme. It's a cosmic baby boom, with stars popping up faster than popcorn in a microwave. How do they manage this stellar sprint? It's all about the gas. These galaxies were stuffed with cold, dense clouds of hydrogen and helium, prime star-making fuel. Unlike today's galaxies, where gas is diluted and mixed with heavier elements, the early universe offered a pure, concentrated supply. With no brakes on, stars ignited like wildfire. Plus, the scarcity of metals, elements heavier than helium, meant less cooling, leading to massive scorching stars, dozens or even hundreds of times the sun's mass. These behemoths burned bright and died fast, exploding as supernovae and leaving behind a legacy of chaos and light. The chemistry of cosmic infants, a pristine recipe. Let's zoom into their chemistry. The farthest galaxies are elemental minimalists, built almost entirely from hydrogen and helium, the Big Bang's original ingredients. Compare that to the Milky Way, a cosmic melting pot brimming with carbon, oxygen, iron, and more, forged over billions of years by countless stars. In astronomer lingo, those heavier elements are metals, and in the early universe, metals were as rare as a unicorn sighting. Why? Not enough stars had lived and died to sprinkle the cosmos with their ashes. This metal scarcity shapes everything. Without metals to cool the gas, stars in these galaxies likely grew bigger and hotter than today's typical suns. Some might even be the fabled Population 3 stars, the universe's first stellar generation, made purely of hydrogen and helium. These giants, potentially hundreds of solar masses, would have been short-lived cosmic fireworks blasting out the first metals when they exploded. Finding evidence of them would be like uncovering the universe's birth certificate, a snapshot of its earliest days. Colors of the cosmos, a glimpse through infrared eyes. What do these galaxies look like up close? Through JWST's infrared vision, they're faint, reddish smudges, hardly glamorous at first glance. But that redness tells a story. Their light, originally ultraviolet from hot young stars, has been stretched by the universe's expansion into the infrared by the time it reaches us. If we could see them in real-time visible light, they'd blaze with a youthful glow, like a neon sign in the cosmic dark. JWST acts like a translator, turning their ancient heat into images we can grasp. Zoom in, and the details get weirder. Many show bright cores of star formation, surrounded by fainter halos of gas and dust. Some hint at embryonic structures, tiny disks, bars or clumps, suggesting they're just starting to organize. It's like watching a rough sketch evolve into a masterpiece, one messy stroke at a time. The colors and shapes paint a picture of a universe in flux, teeming with raw potential. Comparing to local galaxies, a galactic glow-up. To really get these cosmic infants, let's stack them up against galaxies we know. The Milky Way. Our home galaxy is a grand spiral with swirling arms, a bulging center, and a supermassive black hole keeping it all in check. It's a seasoned veteran, 13 billion years in the making, with stars of every age and flavor. The farthest galaxies? They're the Milky Way's distant cousins, small, chaotic, and metal poor. They're the raw dough that, through eons of kneading and baking, became the galactic bread we live in. Andromeda, M31. Our nearest big neighbor, Andromeda, is another spiral titan, slightly larger than the Milky Way. It's a calm, mature galaxy with star formation mostly in its arms. The farthest galaxies, by contrast, are all in star factories, with activity everywhere in their tiny frames. It's like comparing a quiet suburb to a bustling startup hub. One's settled, the other's pure energy. Dwarf galaxies. Even local dwarf galaxies like the small Magellanic Cloud don't match these ancient oddballs. Dwarfs are small and irregular, sure, but they are still bigger and richer in metals than their cosmic forebears. The farthest galaxies are the true originals, fresh, unpolished, and untouched by time. The human element, astronomers' cosmic quest. Behind these mind-blowing finds are astronomers who live for this stuff. When JWST beamed back images of galaxies at Z equals 13 and beyond, jaws dropped. It's like flipping through the universe's baby album. One scientist marveled. Another laughed. We had theories, but the universe loves throwing curveballs. These folks spend sleepless nights poring over data, tweaking models, and chasing the next big discovery. It's not just science. It's a passion-fueled adventure to decode our origins. Why it all matters. As we close out Part 5, we've seen the farthest galaxies as small, chaotic powerhouses, wildly different from today's cosmic lineup. But why should we care? What do these oddballs tell us about the big picture? In Part 6, we'll uncover how they shaped the cosmos, from re-ionization to the birth of black holes. It's a cosmic detective story you won't want to miss. Alright everyone, in Part 5, we zoomed in on the farthest galaxies, those scrappy, chaotic infants that defy our expectations of what galaxies should look like. They're not the majestic spirals or stately ellipticals we're used to. They're raw, untamed, and bursting with energy. But here's the million-dollar question. Why do they matter? What can a faint smudge of light, shining from 13 billion years ago, possibly tell us about the universe today? Now, in Part 6, we're diving into the why, unpacking how these distant galaxies are rewriting the cosmic story, from the universe's first flickers of light to the sprawling web of galaxies we call home. Buckle up for a journey through time, space, and the very essence of existence. Part 6. Unlocking the universe's secrets. Why farthest galaxies matter. Time capsules from the cosmic dawn. Let's kick things off with the mind-blowing reality of these galaxies. They're ancient beyond imagination. When we observe a galaxy 13 billion light-years away, we're not seeing it as it is now. We're seeing it as it was 13 billion years ago, when the universe was just a toddler, barely a few 100 million years old. Think of it as peering through a cosmic telescope, one that doesn't just magnify space but rewinds time. These galaxies are like baby photos of the universe, snapshots of its earliest days, preserved in light that's been traveling across the cosmos ever since. Why does this matter? Because these time capsules let us study the universe's infancy up close. After the Big Bang, the cosmos was a hot, dense soup of particles, quarks, electrons, and photons swirling in a chaotic dance. As it cooled, atoms formed, and eventually, gravity began sculpting the first stars and galaxies. These farthest galaxies are the closest we'll ever get to witnessing that process in action. They're not just pretty lights. They're laboratories for testing our theories about the Big Bang, the birth of structure, and the physics of a universe under extreme conditions. Imagine being an archaeologist unearthing the first tools of humanity. These galaxies are that, but for the entire cosmos. Fun fact, The light from these galaxies is so old that it's stretched by the universe's expansion, shifting from ultraviolet to infrared. That's why we need telescopes like the James Webb Space Telescope, JWST, to catch it. It's like tuning an old radio to pick up a faint, distant signal. The puzzle of galaxy formation. Next up, let's talk about how these galaxies challenge everything we thought we knew about galaxy formation. The classic picture was simple. Gas clouds collapse under gravity, stars form slowly, and over billions of years, galaxies take shape. It's a tidy story, except the farthest galaxies don't fit it. Many are brighter, bigger, and more active than we expected for their age. It's as if you found a toddler lifting weights and reciting poetry. Impressive, but it makes you question your whole understanding of how kids grow up. Take JD's GSS 14-0, a galaxy spotted by JWST at a redshift of Z equals 14.32, meaning its light left it when the universe was just 300 million years old. This galaxy is a cosmic overachiever, glowing with a brightness that suggests it's already packed with stars. How did it get so big, so fast? One possibility is that the first stars were giants, hundreds of times more massive than our Sun. These behemoths burned hot and fast, exploding as supernovae and scattering heavy elements that fueled the next wave of star formation. Another theory points to baby black holes, gobbling up gas and triggering bursts of star birth. Either way, these galaxies are forcing us to redraw the timeline of cosmic evolution, adding a thrilling twist to the story. Here's a thought to chew on. If galaxies formed faster than we thought, what does that say about the universe's early conditions? Were they more chaotic, more fertile than our models predict? The answers are still out there, waiting in the light of the next distant galaxy we find. Re-ionization, lighting up the universe. Now, let's dive into one of the universe's most dramatic transformations. Re-ionization. Picture the scene after the Big Bang. The universe is a dense fog of neutral hydrogen, opaque to light, like a room shrouded in thick mist. Then, around 400 million years after the Big Bang, something incredible happens. The first stars and galaxies ignite, their ultraviolet light ripping electrons from hydrogen atoms, ionizing the gas and making the universe transparent. It's like flipping on a chandelier in a pitch-black ballroom, suddenly revealing the walls, the floor, and every glittering detail. The farthest galaxies are the prime suspects in this cosmic makeover. Their light holds clues about when and how re-ionization unfolded. Were they numerous enough, bright enough to flood the universe with UV rays? JWST's observations suggest yes. These galaxies were likely the heavy lifters, their fierce star formation driving the process. But there's a mystery. Some models predict we should see even more of these galaxies to fully account for ionization. It's like finding a few candles in a dark room and wondering if there's a hidden spotlight we haven't spotted yet. Astronomer Richard Bowens puts it this way. These galaxies are the unsung heroes of the early universe, turning on the lights so the cosmic show could begin. Their role in reionization isn't just a historical footnote, it's a cornerstone of how the universe became the place we know today. The seeds of the cosmic web. Zoom out a bit, and these galaxies reveal something even more awe-inspiring. The origins of the cosmic web. Today, galaxies aren't scattered willy-nilly. They're woven into a vast tapestry of filaments, walls, and voids, all held together by the invisible threads of dark matter. This cosmic web is the universe's architecture, and it started with the farthest galaxies. These early galaxies formed in the densest pockets of dark matter. Think of them as seeds planted in the richest soil. Over billions of years, gravity nurtured these seeds, pulling in more gas and galaxies, growing them into the clusters and superclusters we see now. By mapping these distant galaxies, we can trace the web's first threads, watching the universe evolve from a nearly uniform haze to a structured masterpiece. It's like watching a time lapse of a forest growing. Each galaxy, a tiny sapling that becomes a mighty oak. Here's a wild stat. The cosmic web spans billions of light years, but its roots lie in galaxies that were once just a few light years across. From humble beginnings come cosmic giants, dark matter and dark energy, the invisible puppeteers. Speaking of dark matter, these galaxies are gold mines for understanding the universe's hidden forces. Dark matter, making up 27% of the universe's mass energy, is the unseen scaffold that shapes galaxies. By studying how these early galaxies cluster and move, we can map dark matter's influence in the young universe. It's like tracing a riverbed by watching how the water flows. Then there's dark energy, the mysterious force accelerating the universe's expansion. By measuring the distances and redshifts of these galaxies, we can chart how fast the universe has been stretching over time. This pins down dark energy's behavior, which still baffles physicists. Are we headed for a big freeze where expansion dilutes everything into a cold, dark void? These galaxies hold pieces of that puzzle. Every distant galaxy we study is a vote in the cosmic election of dark energy's fate, says cosmologist Daniel Eisenstein. Their light isn't just beautiful, it's a ballot in the universe's biggest mystery. Quotes from the experts. Let's hear from the stargazers themselves. These galaxies are like fossils from the universe's dawn, says astrophysicist Charlotte Mason. They're the building blocks of everything. Stars, planets, even us. Brant Robertson adds, each new discovery pushes the boundary of what we think is possible. The universe keeps surprising us, and that's what drives us forward. Their words echo the thrill of this cosmic chase. It's not just science, it's a story, and we're all part of it. As we close part 6, we've seen how the farthest galaxies are more than distant lights. They are the keys to the universe's deepest secrets. But this journey wouldn't be possible without the tools that bring these galaxies into focus. In part 7, we'll explore the machines and minds that make this cosmic detective work happen. Get ready for a backstage pass to the tech rewriting history. Alright guys, in part 6, we uncovered how these distant galaxies are like cosmic time machines, revealing secrets from the universe's wild, formative years. But none of this would be possible without the incredible technology that lets us peer across billions of light years. Now, in part 7, we're diving deep into the tools that make this cosmic detective work possible. From legendary telescopes like Hubble and JWST to the clever techniques astronomers use to spot the faintest, most distant galaxies. Get ready for a backstage pass to the tech that's rewriting the history of the universe. Part 7. The tech that took us there. Telescopes and beyond. The telescope titans, Hubble and JWST. Let's start with the heavyweights of astronomy. Space telescopes. These aren't your backyard stargazing tools. They're high-tech marvels orbiting hundreds of miles above Earth, free from the atmosphere's blurry mess. First up is the Hubble Space Telescope, launched in 1990. and still going strong after more than 30 years. Hubble's been a game changer, capturing jaw-dropping images like the Hubble Deep Field, where a tiny patch of sky revealed thousands of galaxies stretching back billions of years. It's like aiming a camera at a blank wall and discovering a hidden mural of cosmic history. But Hubble has its limits. It mostly observes in visible, ultraviolet, and near-infrared light, which is great for nearby galaxies but struggles with the farthest ones. Why? Because the light from those distant galaxies is stretched by the universe's expansion into longer, redder wavelengths, beyond what Hubble can easily see. It's like trying to tune into a radio station that's just out of range. You get static instead of the full song. Enter the James Webb Space Telescope, JWST, launched on Christmas Day, 2021. If Hubble is the trusty old detective, JWST is the slick, high-tech rookie with all the gadgets. Its primary mirror is a massive 6.5 meters across, 3 times wider than Hubble's, and made of 18 gold-coated segments that unfold in space like a cosmic flower. Gold? Yep, because it reflects infrared light better than silver or aluminum, making JWST a heat-seeking missile for ancient galaxies. And to keep its instruments icy cold, a must for detecting faint infrared signals. JWST orbits 1 million miles from Earth at a spot called L2, using a sunshield the size of a tennis court to block the sun's warmth. It's like a cosmic ninja staying in the shadows to catch the universe's oldest whispers. How telescopes work? The basics. So how do these telescopes actually work? At their core, telescopes are giant light buckets. They collect as much light as possible from distant objects and focus it into an image. The bigger the mirror, the more light they can gather, and the fainter the objects they can see. That's why JWST's 6.5-meter mirror is such a big deal. It's like upgrading from a kiddie pool to an Olympic-sized one. But it's not just about size. Telescopes also need to be precise. Hubble's mirror is polished to within a fraction of a human hair, and JWST's is even finer, with each segment adjustable to nanometer accuracy. It's like tuning a guitar string to the perfect pitch, but for light waves. And then there's the issue of Earth's atmosphere, which smears light like a foggy window. That's why space telescopes are so powerful. They float above the turbulence, giving us crystal clear views of the cosmos. Spectroscopy, the cosmic decoder. Telescopes don't just take pretty pictures, they also decode the universe's secrets through spectroscopy. This technique splits light into a rainbow, revealing the unique signatures of elements like hydrogen, oxygen, or carbon. It's like scanning a barcode to see what's inside a product. For distant galaxies, spectroscopy is crucial for measuring redshift, which tells us their distance and age. Here's how it works. Every element has a distinct pattern of lines in its spectrum, like a fingerprint. As a galaxy speeds away from us, these lines shift toward the red end of the spectrum. By measuring that shift, astronomers calculate the galaxy's redshift z, and thus its distance. For nearby galaxies, this is straightforward. But for the farthest ones, the light is so faint that it's like trying to read a book by the glow of a single firefly. That's where JWST's near-infrared spectrograph, NIRSpec, shines. It can capture spectra from dozens of galaxies at once, with sensitivity that Hubble could only dream of. Gravitational lensing, nature's telescope. But wait, there's more. Astronomers have a clever trick up their sleeves called gravitational lensing. This phenomenon, predicted by Einstein, happens when a massive object, like a galaxy cluster, bends and magnifies light from a more distant galaxy behind it. It's like using a cosmic magnifying glass to make faint galaxies brighter and easier to study. Without lensing, some of these distant galaxies would be too dim to detect, even with JWST. Take the galaxy MAX 0647-JD, spotted at a redshift of Z approximately 11. Its light was amplified by a massive cluster's gravity, making it visible to Hubble. JWST is now using lensing to push even deeper, finding galaxies at Z equals 13 and beyond. It's a bit like cheating, but hey, the universe doesn't play fair. Why should we? Ground-based giants, the unsung heroes. Space telescopes get all the glory, but let's not forget their ground-based cousins. Telescopes like the Keck Observatory in Hawaii or the Very Large Telescope, VLT, in Chile are monsters with mirrors up to 10 meters wide. They can't escape the atmosphere, but they make up for it with sheer size and cutting-edge tech like adaptive optics, which uses lasers to correct for atmospheric blur in real time. It's like giving the telescope a pair of high-tech glasses that adjust on the fly. These ground-based behemoths are perfect for follow-up observations, like measuring precise spectra or tracking galaxy movements. They work hand in hand with space telescopes, filling in the gaps and providing a multi-wavelength view of the cosmos. It's a cosmic tag team, with each tool playing to its strengths. The human element, dreamers and doers. Behind every telescope is a team of humans driven by curiosity. Take the Hubble Space Telescope. It took decades of planning, engineering feats, and even a daring space shuttle mission to fix its blurry mirror. The JWST? It was a 20-year saga, with thousands of scientists, engineers, and technicians working across continents to make it happen. There were delays, budget overruns, and nail-biting moments, like when JWST's sunshield snagged during testing, but the team persevered. And then, there are the astronomers who pore over the data, often working through the night to catch a glimpse of a galaxy's spectrum. It's like panning for gold, says one researcher. You sift through mountains of data, hoping for that one nugget that changes everything. Their passion and grit are what turn raw photons into cosmic breakthroughs. Future tech. What's next? The tech doesn't stop here. In the coming years, we'll see even more powerful tools, like the Nancy Grace Roman Space Telescope, set to launch in 2027. With its wide field view, Roman will map the universe's structure on a massive scale, complementing JWST's deep dives. And on the ground, the Extremely Large Telescope, ELT in Chile, will boast a 39-meter mirror, 4 times wider than anything today. It's like upgrading from a compact car to a monster truck for stargazing. These future telescopes will hunt for even fainter galaxies, potentially at redshift Z equals 15 or beyond, inching closer to the Big Bang's first light. They might even spot the elusive population 3 stars, the universe's first stellar pioneers. The possibilities are endless, and the cosmos is just waiting to spill its secrets. As we wrap up part 7, we've seen how technology is the backbone of our cosmic quest, turning the impossible into the possible. But what's next? In part 8, the future of cosmic exploration. What lies beyond? We'll gaze into the crystal ball of astronomy, imagining the discoveries that await us. From Z equals 15 galaxies to the hunt for life's origins, the best is yet to come. Let's go. So, in part 7, We marveled at the cutting-edge technology, like the James Webb Space Telescope, JWST, and gravitational lensing that's allowed us to peek billions of years into the past, witnessing galaxies as they were when the universe was in its infancy. But now, it's time to shift our gaze from the past to the future. What's next in our relentless quest to unlock the universe's deepest secrets? From chasing galaxies born at the dawn of time to probing the enigmatic forces of dark matter and dark energy, the future of cosmic exploration promises to be both dazzling and mind-bending. So, buckle up for Part 8, where we'll peer into the astronomical crystal ball and envision the breakthroughs that lie ahead. The universe is whispering its mysteries. Let's listen closely. And if you made it this far, thank you so much. Please sub for more videos coming soon. Part 8. The future of cosmic exploration. What lies beyond? Pushing the redshift limit. Galaxies at Z equals 15 and beyond. Let's kick things off with the ultimate cosmic treasure hunt, tracking down galaxies that formed even closer to the Big Bang than we've ever seen before. The JWST has already shattered records, spotting galaxies at a redshift of Z equals 14.32, meaning their light began traveling to us just 290 million years after the universe's birth. That's incredible, but astronomers are hungry for more. The next frontier? Galaxies at Z equals 15, Z equals 16, or even higher. Objects so ancient, they emerged during the cosmic dark ages, a shadowy epoch when the first stars began to spark into existence. Why does this matter? These ultra-distant galaxies could hold the key to finding the universe's first stars, known as population 3 stars. Picture these as stellar titans, hundreds of times more massive than our Sun, forged solely from the primordial elements of hydrogen and helium. They burned fiercely, lived briefly, and died in spectacular supernova explosions, scattering the first heavy elements like carbon and oxygen across the cosmos. Discovering these stars would be like unearthing the universe's birth certificate, offering a direct glimpse into the chaotic aftermath of the Big Bang. Upcoming telescopes like the Nancy Grace Roman Space Telescope and the Extremely Large Telescope, ELT, are being designed with this goal in mind, boasting the sensitivity to detect the faint glow of these primordial beacons. Imagine standing at the edge of time itself, peering into a realm we've only dreamed of. It's a leap into the cosmic abyss, and we're almost ready to take it. But the challenge is immense. At such extreme redshifts, the light from these galaxies is stretched into the infrared, dimmed by distance and cosmic expansion. It's like trying to spot a candle flame from across an ocean. Future missions will need to combine ultra-precise instruments with innovative techniques, like using galaxy clusters as natural magnifying glasses via gravitational lensing to bring these faint flickers into focus. The payoff, though, could redefine our understanding of how the universe transitioned from darkness to light. The quest for the first black holes. Galaxies aren't the only ancient relics we're after. The early universe was also a nursery for the first black holes, tiny seeds that eventually ballooned into the supermassive giants we find at the hearts of modern galaxies. How did these cosmic infants come to be? Did they form from the direct collapse of massive gas clouds? Or were they the remnants of those explosive population 3 stars? The JWST, alongside future missions like the Lynx X-ray Observatory, is hot on the trail, searching for the telltale X-ray and infrared signatures of these fledgling black holes. It's akin to catching a glimpse of a dragon's egg just before it hatches into a roaring galaxy-shaping beast. And here's where it gets even wilder. Some theorists propose that a few of these early black holes could still be roaming the universe as primordial black holes. If we detect them, they might solve long-standing puzzles like the nature of dark matter or the whereabouts of the universe's missing mass. Picture a swarm of invisible wanderers forged in the Big Bang's fires, silently shaping the cosmos for billions of years. The search for these elusive objects will require not just powerful telescopes, but also creative thinking, perhaps pairing X-ray observations with gravitational wave detectors like LISA to pinpoint their presence. The stakes are high and the rewards could be astronomical. Mapping the cosmic web, from seeds to superclusters. Now, let's zoom out to the big picture. The cosmic web, the universe's sprawling framework of filaments, walls, and voids. This intricate structure is the scaffolding upon which galaxies are strung, like pearls. And the farthest galaxies we've observed are its humble beginnings, the tiny seeds that blossomed into today's massive galaxy clusters and superclusters. Understanding how this web evolved is like piecing together a 3D jigsaw puzzle spanning billions of years. Future telescopes, such as the Roman Space Telescope, are set to revolutionize this effort by mapping billions of galaxies across vast swaths of space and time. With their wide-field cameras and deep sensitivity, these instruments will create a cosmic atlas of unprecedented detail, revealing how gravity wove the universe's threads over eons. Add in the power of artificial intelligence and machine learning, and we'll sift through this deluge of data at lightning speed, spotting patterns like unexpected voids or overdense regions that could hint at new physics. Imagine a map so detailed it shows not just where galaxies are, but how they danced into place across cosmic history. That's the future we're building toward. Dark matter and dark energy, cracking the code. No discussion of the cosmic future would be complete without tackling the universe's two greatest enigmas, dark matter and dark energy. Dark matter, comprising 27% of the universe's mass energy, is the unseen glue that binds galaxies together, while dark energy, making up 68%, is the mysterious force accelerating the universe's expansion. Together, they dominate the cosmos, yet we know almost nothing about their true nature. They are the invisible puppeteers of reality, and the farthest galaxies are our best tools for studying their strings. These distant galaxies act as cosmic lighthouses, their light warped by gravitational lensing to reveal dark matter's hidden presence. By analyzing these distortions, we can map dark matter's web-like distribution, inching closer to understanding its composition. Could it be a new particle, like the elusive axion, or something stranger? Meanwhile, measuring the distances and velocities of these galaxies lets us trace dark energy's influence, showing how it's stretched space over time. Missions like the Euclid telescope are purpose-built for this task, promising the most precise map of the universe's expansion yet. But the real prize lies beyond mapping, identifying what dark matter and dark energy actually are. Are they tied to quantum fields, exotic particles, a flaw in our understanding of gravity? Each new galaxy we study brings us closer to cracking this code, potentially rewriting physics as we know it. It's a high-stakes chase through the shadows, guided by the faint glow of the universe's oldest light. The search for life's origins. Let's push the boundaries even further. Could these distant galaxies tell us something about the origins of life? It's a bold question, but not as far-fetched as it sounds. The early universe was a chemical crucible, with the first stars forging the building blocks of life: carbon, oxygen, nitrogen, through their fiery deaths. By studying the farthest galaxies, we can trace this chemical evolution, watching the cosmos transform from a barren sea of hydrogen and helium into a rich tapestry capable of supporting planets, atmospheres, and perhaps life itself. While these ancient galaxies are too chaotic and youthful to host complex life, they set the stage for everything that came later. Future spectrographs on telescopes like the Extremely Large Telescope could analyze their light, revealing the abundance of life-essential elements and hinting at when and where the conditions for life might have emerged. It's a cosmic genealogy, linking us to the first stellar furnaces that made our existence possible. And who knows, maybe life got an earlier start elsewhere, sparked by the chemistry of those primordial galaxies. We're all star stuff after all, born from the universe's earliest embers. Behind every leap into the cosmos are the humans who make it happen. The future of exploration isn't just about telescopes and data. It's about the dreamers who design them, the scientists who decipher their signals, and the storytellers who bring the wonders to life. From the engineers who folded JWST's sunshield like origami, to the astronomers burning the midnight oil over redshift calculations, this is a shared odyssey. With projects like the ELT and Roman Space Telescope on the horizon, we're entering a golden age of astronomy, where curiosity turns the impossible into reality. As Neil deGrasse Tyson wisely said, the universe is under no obligation to make sense to you, but that doesn't mean we stop trying. It's this relentless spirit that will carry us forward, fueled by a blend of technology, ingenuity, and wonder. As we wrap up this video, we've journeyed from the farthest galaxies to the very edge of human knowledge. But this isn't the end. It's a launchpad. The universe is vast, unpredictable, and brimming with secrets, and we're only beginning to scratch its surface. So keep your eyes on the stars, keep asking questions, and remember, the greatest discoveries are still out there, waiting in the cosmic void for us to claim them. We appreciate all the subs. Thank you guys so much. Have a good day.